Hey guys, if you guys can turn to page 2. Okay, page 2 in your packets. Let me do a recap of what we covered so far on page 2. First, we start off with this relationship here. G of x is as the definite integral from -3 to x of f of t. Whenever we see this, that indicates that f is really sitting at the derivative level of g, okay? Because it takes an integral to impact f in a way that will make it equal to each other. So we know that f is not the same level as g. F is really sitting at a level below. F is the derivative. So understand that you're looking at the f graph, but you're also looking at the g prime graph, okay? So it says find g prime and g double prime. So g prime is f of x, so we are able to assign that relationship there. And then also, you can go through second theorem and show that the derivative of this notation will give us f of x times 1, right? We know derivative and integrals will undo and cancel each other out. Okay, all we do is we plug the upper bound into the function, so it's f of x times upper bound's derivative, so times 1. So we know that's why g prime is equal to f of x. So if I want to find g double prime, that means I'm going a derivative level down from g prime to g double prime. So I'm also going to go down a derivative level for f to f prime. So here we have 3 tiers of relationships here we're going to use for part B. Okay. So then part B, we said find g of 0. So to find g of 0, we go to our definition. Our definition says replace the upper bound with the x value. So I'm going to replace x with 0. So the definite integral from -3 to 0, I look at the graph. The graph just shows me a geometric shape, trapezoid. I can also think of it as a triangle on top of a rectangle. I can find those areas, add them together, and I get 4.5. Okay. If I want to find g prime of 0, g prime of 0 is f of 0. So f of 0 is a point that sits on the graph. F of 0 is 1. So that's why g prime of 0 equals 1. If I want to find g double prime of -1, that in relation to f is f prime of -1. -1 is here, but f prime of -1 is asking for the rate of change of that point, which is essentially slope. So it's a nice diagonal line, which means that we can find the slope of this line. The slope of this line is going to be the same all the way through. So I just do rise over 1, down 1 over 3, -1/3. Okay. Any questions so far, A and B? Okay, so now part C says find all the values on the open interval where G attains a relative max. So relative max, we have to basically understand that this is not the G graph, this is the G prime graph. So we started labeling our derivative graph, right? Anything above is positive slope, below is negative slope. On the x-axis is slope 0. So our critical points are -4, 1, and 3. So -4, 1, and 3. And now we just want to look, where is the graph located? Is it above or below the x-axis? Don't look at whether it's rising or falling. That's concavity, okay? So we see that the first region here between -5 and -4 is below the x-axis, so therefore decreasing. Between -4 and 1, above the x-axis, therefore increasing. From 1 to 3, above the x-axis, increasing. Between 3 and 4, below the x-axis, decreasing. So if we look at this sign line, we know that there must be a relative max where? At 3, because G prime changes from positive to negative. Okay. So I'm just going to put that sign line down here because we're going to reference it for the next part. So part D says find the absolute minimum value of the G graph. So absolute minimum value, anytime you see absolute max, absolute min, that's extreme value theorem. Okay, that's a we covered that in the first semester. So as a reminder, extreme value theorem says if I want to find absolute max, absolute min, I just have to identify the candidates and test the candidates. Okay, so EVT, that means you're going to test endpoints, and you're going to test relative max and mins. Okay, so those are the only places that you can ever have an absolute max or absolute min, right? There's no other candidates that we have to worry about. So we're definitely going to test -5 and 4. We have relative min at -4. We have relative max at 3. But why in this case can we maybe not worry about 3? Does 3 have a chance of being an absolute minimum? Right. There's no chance that a relative max could ever be the lowest point on the graph, right? So we can kind of avoid that. If it's asking for absolute extrema, that means it's both max and min, then we will test -4 and 3. But as it stands, let's just test -5 and 4 because those are the endpoints, and we'll test -4 because the relative min could end up being the absolute min. Okay, so we're going to test 3 points here. So we'll test G of -5, we'll test G of -4, and we'll test G of 4. Okay, so the way we're going to find these values is we're going to go back to our rule, right? Our rule is telling us how to find any location on the G graph, -3 to x. So all we're going to do is replace the upper bound with our x value. Now, what do you notice about the bounds here? Yeah, upper bound is lower. Now, we always want to follow the rule, right? So we don't want to make the adjustment until we follow the steps exactly, because they always tell us here upper bound is defined with the upper bound being the variable. So normally, now if it was a power rule problem and you're just going through your calculus steps, it doesn't really matter if the bounds are out of order. If that's what they give you, then you keep it that way. But if you're trying to look at a graph, then I think it's beneficial to allow for the bounds to be organized in a way so that everything is more straightforward. So here, because I'm having to read the graph, I would prefer to flip the bounds. So if I flip the bounds, I need to make an adjustment. I need to pull a negative out in front. Okay, so what's the depth integral from -5 to -3? All right, so let's total those regions up, right? So -5, -3. Remember that you may be seeing different shapes as you're looking at this graph, but the only thing that you care about is what's between the graph and the x-axis. So let me just kind of show you that any other shape that you're looking at is not going to be part of our graph. We only care about what's between the graph and the x-axis. Okay. All right, so between -5 and -3, this is an area of 1/2 base times height. So 1/2 1 times 2, that's going to be a -1. This over here, 1/2 base times height, 1/2 1 times 2, that's a +1. So what's the region going to add up to be between -5 and 3? Yeah, 0. Yep. -0 is still 0, so 0. All right. Next up, let's find our second candidate from -3 to -4. The bounds are out of order. We prefer to read from left to right, so I'm going to flip the bounds. And change the sign. Okay, so what's the depth integral from -4 to -3? 1, okay, we'll put 1 down, but there's a negative that we have to keep track of, so that's going to end up giving us -1. Okay, G of 4. Okay, in this case, the bounds are already in order, so we don't have to make any adjustment. Okay, we look at our graph from -3 to 4. Everything looks pretty straightforward, but this seems a little strange here. That by itself is not a geometric shape, but maybe it's a combination of shapes. What could we do to get to the area of that strange little region? Any ideas? Good. So if you think about an area of a rectangle, right? We see a rectangle there. If we subtract out the area of the semicircle, then what remains are these little edge corner regions, right? So there's a triangle here that you can imagine, right? A triangle minus a semicircle will give us that little shaded region. So the rectangle is width times height. 2 times 1 is 2. Yeah. And then the area of the semicircle, what's the radius of the semicircle? 1, so 1/2 pi r squared, 1/2 pi 1 squared. And that's just going to get us 2 minus pi over 2. Okay, it's above the x-axis, so we can keep everything the same sign. Okay, and the area here, this is 1/2 minus 1/2, so that's going to cancel out to be 0, right? So -4 to 3, sorry, -3 to 4, 4.5 plus 2 minus pi over 2 plus 0, right? Because those two will cancel out, 1/2 and -1/2. Okay, so pi over 2 is around 3/2, around 1.5. So 6.5 minus 1.5 is around 5. So now we just compare these y values, right? We're looking for an absolute minimum. These are the only candidates we're looking at. So the lowest y value that we see is -1, so that must be our absolute minimum. Absolute min is -1. Okay, part E, find all the values in which the graph has a point of inflection. So point of inflection, we're going to look at our derivative graph, right? How do we find points of inflection looking at the derivative graph? Well, the x-axis will be where the slope is 0. Yeah, peaks and valleys, okay? So peaks and valleys of your derivative graph is going to be where your points of inflection is going to live, okay? So points of inflection at -3, 1, and 2. From -5 to -3, now we look at the slope. Okay, the slope of my derivative graph is going to translate to concavity, right? So positive slope is concave up, negative slope is concave down, concave up, concave down. Don't look at the curvature. This is not the original graph. This is the derivative graph, so just look at the slope. Okay, so point of inflection must be at -3, 1, and 2, because that's where our G double prime changes signs. Okay, let's skip over to page 6, and this is going to be a calculator-heavy problem. You can have your calculator sheet out, and I'll go over the steps for both the graphing and the 36 Pro, and I'll walk around and see if you guys have any questions. Okay, so go to page 6. Okay, does anybody still need this page? Okay, page 6. Okay, an object moving along a horizontal line, V of t. Okay, I'll do the graphing calculator first, and then I'll talk about the steps for the scientific one. Okay, you want to type in your velocity function. Notice that there's trig involved, so make sure that your mode is always in radian mode. Okay, make sure you're in radian mode. Okay, go to y equals, type in that function, 4 sine of x squared minus 2x plus 2. Don't use variable t, always use variable x. Okay. And it says set the window values to -1, 5 for x min, x max, and then for y min, y max, go from -6 to 6. It just makes it easier to have the window set to see everything we need to see. So if you go to window, it's next to y equals, and just change those boundaries there. X min, make it -1, x max, make it +5. Y min, make it -6, and y max, make it +6. Okay, so now go to graph. I graph is from previous period, so that's why it's already up. Okay, hit graph. Now it says find when the object is motionless. So object is motionless is when velocity is what? 0. So we're looking for x-intercept. Okay. So on your calculator sheet, I have the steps here for x-intercept, and I'll go through the steps here, and then we can try it. You're going to go to second trace 0. Second trace 0 is going to help find you that x-intercept feature. You're going to make the calculator find that x-intercept for you. So as you move your cursor, you're going to start off by moving the cursor to the left of the x-intercept, hit enter. Then you'll move over to a point on the right of the x-intercept, hit enter. And then the calculator will now know, okay, you want me to look between these 2 points. It's going to look between those 2 points that you gave it, and it's going to look for the x-intercept on its own. Okay, so let's try that. Go to second trace, and then select the 0 feature. Left bound, so I'm going to scroll over to a point on my first x-intercept. We're only going from 0 to 4, so we're going to ignore that x-intercept. I'm going to pick a point to the left of this x-intercept. And you see that question mark there, left bound question mark. So basically the calculator is asking, give me a left bound. Just choose a point to the left of the x-intercept. Never put your cursor directly on the x-intercept and hit enter. Then the calculator is going to get confused. It's not going to know where you want it to look. So pick a point to the left, hit enter, and it says right bound. So now you're going to use your directional arrow, move to the other side of the x-intercept, hit enter again. Doesn't matter where, just as long as it's relatively close and not directly on the x-axis, hit enter again. And then you see that question there, says guess question. That means it's asking, okay, are you ready for the calculator to guess your x-intercept? Hit enter again. And now it's going to find that x-intercept for you, 2.463. Now there's a strange notation there. That 4e to the -13 is basically saying it's really close to 0. It's basically, it'd be nice if it just rounded to 0, but for some reason the calculator is showing that funny notation. But that's basically saying it's 0. Okay. So that's the first x-intercept. Okay. You repeat the process for the other x-intercepts as well. Okay. And as you do that, I will go and show the steps for the scientific calculator. So you try that again, go to second trace, and you find another x-intercept, pick a point to the left and to the right, and you should get 3.298. Okay, so try that for the other two while I show the 36 Pro. So 36 Pro, on your calculator sheet, there is an estimate x-intercept. Okay. What you're going to do is we're going to enter the function directly into table first. So go to table and edit function. So table, edit function. Type in your function. Make sure that you are in radian mode. Right? If you go to mode, that you are double checking your radian mode. Type in 4 sine, parentheses, x squared minus 2x plus 2. Now, just understand that if you're using 36 Pro, it's going to be a little more cumbersome because it is not going to be able to give you a visual graph. So you really just have to rely on the table of values. Okay, so table setup, you're going to start at 0 because That's the start of our interval. And then step, you can do 0.01. It just takes a long time. Maybe we can say that for later. So maybe start off maybe doing 0.1 instead. Okay, start off with 0.1. It may still take a while to scroll down, but what's going to happen is it's going to give you every order pair by increments of 0.1. And what you're trying to do is you're looking at your y values to see when is the y value going to change signs. Wherever the y value changes signs, it's an indication that that's where the x-intercept is. Okay. Make sure you're on auto. Okay. You want the table of values to auto-populate. Hit enter, enter. Okay. It may take a while here. You're going to scroll down. You're looking at the y values and you're trying to see when is that y value going to change signs. It's still sitting at 3. And I see, okay, there it is. There's a change in sign between 2.4 and 2.5. You see that? So we know that we're close. We know that around 2.4, 2.5 is where our x-intercept is. Now we're going to get more accurate here. So go to table, edit function, and then we're going to make the step even smaller, 0.01. Okay, if you do 0.01 and you can start at 2.3, that's good. That means I have to scroll as far. And now you see that your y value is hitting negative right around 2.46. Yeah, 2.46. Okay. And if you want to get even more accurate to 3 decimal places, you can just go back and change your step to 0.001. Okay, you're basically starting around 2.45, so it shouldn't take it too much longer to scroll. You should be able to get to 3 decimal places pretty accurately. There we go. It changes signs right around there, so it's 2.463 is really accurate. That's as good as you're going to get on the graphing calculator as well. So you're repeating the process until you find all your x-intercept. There's a change in sign, so it says when does the object change direction? There's a change in sign at all those x-intercepts, so you can say 2.463, 3.299, and 3.903. Okay. We know the positive and negatives because we look at the velocity graph to see up until the first x-intercept, the graph is above the x-axis, so that's positive velocity, negative velocity, positive, and negative. Okay, let me come around and see, are there any questions? Anybody having trouble with keystrokes or entering something into the calculator? Oh, okay, you want this back. Is anybody else missing yesterday's packet? Yeah. For some reason,
If our numbers are a little off, is that okay?
How far off?
Like I got 3.297.
Yeah. Are you using that second trace feature?
Yeah.
You are? Huh.
So,
I guess either I'm a little off. So that's fine then. I thought it was 3.298. Okay, that's fine. As long as you're going through that step, that's sufficient. Okay, so we're good with that, hopefully. Next up says find the velocity of the object at t equals 3 seconds. So the velocity, you're just entering 3 directly into the function. There's no calculus involved. But you can do a little bit of a shortcut, right? Since your y is already holding that function, what you could do is you can go to vars y vars function, and then just plug 3 directly in and make the calculator pull that function and plug in the 3 in for you. But you can also do it manually as well. Okay. Velocity is meters per second, so negative 3.836 meters per second. Part D, find the acceleration. We know acceleration is the derivative, so the derivative, you got to use math 8. Go to your derivative feature and make the calculator find the acceleration value for you. So d over dx, type in the velocity function, or you can call it from your variable table, from your variable button, and then x equals 3. So it's going to get you the acceleration value. Your units of measure is going to change, right? 4.539 meters per second squared. Okay. Any questions with calculator so far? Okay. Part E, is the object speed increasing or decreasing? Okay. How can we determine speed increasing, decreasing? What do we look at? Okay. Compare signs between velocity and acceleration, right? So here, different signs means what? Decreasing speed, yeah. Part F, find the total displacement. Total displacement is just a definite integral. So do math 9, get your definite integral notation showing up, and just plug in 0 to 4 of the velocity function. So you're just typing everything in. You're making the calculator do all the work for you. Okay, math 9 from 0 to 4. Again, I'm going to call my velocity function. Now, every time you take a derivative or integral, your units will change. Velocity started off as what? As meters per second. You take the antiderivative, you're stripping away that denominator unit, it's become meters. Okay, so keep that in mind. When we're even when we're dealing with problems that are not particle motion, keep that in mind. Whatever unit you have, if you take the integral, you've got to make that unit change. Okay, that denominator is going to go away. Okay, part G, find the total distance. Total distance is where we got to involve absolute value. So it's the definite integral of the absolute value of v of t. Okay, so practice getting to your absolute value notation. So do math 9, set up your definite integral first. And now go to math, NUM, ABS. Okay, type in your function. It may take a little bit longer, though, for the absolute value to take hold. So you should get 12.178. Again, units of measure will change. We're going to go up to meters now. We're accumulating velocity over the course of these time periods, so that's why we're getting 12.178 meters. Okay, part J, this is where we have to involve this first theorem rearranging. where anytime I'm looking for a physical location and I'm giving a starting location, I need to go through this process. Final position equals initial plus displacement. So I'm starting at location 2, and I want to figure out how much progress do I make in that 2-time interval. So I'm going to set this up. I'm looking for x of 4. I'm starting at x of 0, so I want to know what happens in that gap. I want to know how much ground do I cover between 0 and 4 seconds. And the calculator can do that for us, right? And we found this from part F, right? Displacements. So that means this object is going to start at location 2, and it's going to make a forward progress of 7 units. So that's why he's going to end up at location 9.753, 4 seconds in. Okay, questions there?
You don't even really need to calculate for that.
Right. If it's if we're pulling it from above, but it may not always be that way. If it's not, then you just use the calculator again. Part K, find the average velocity. So average velocity, think of that as average value. So we got to go through average value theorem. 1 over b minus a, integral from a to b of v of t. Okay. We can again pull that information from part F. We get 1.938. Now you may be looking at this going, wait, I started with meters per second, I took the integral, how come I'm still sitting at meters per second? The reason why is, yes, it did turn into meters, but then you're dividing by 4. If you're dividing by 4, you're dividing by time again, so you're back to your original units of measure. So your average value is going to change units, but it's going to change right back because of the divided by 4. So this is the average velocity over that time period from 0 to 4 seconds. Okay, any questions with calculator? Okay, let's go to page 7. See how much of this we can get through. Does anybody still need this? Again, the key is attached to the back of your page here. So I've got keys for all these, all the worksheets we're doing. Okay, let's go to page 7. Okay, Riemann sums. This is a good problem for us to practice here. It says, the important key point I want to keep reminding you is anytime you're doing a calculus process, whether it's derivative or integrals, your units of measure must change. Okay, so keep that in mind. Okay. Now, this is not a particle motion problem, so we can't use language like velocity and acceleration, right? Even if we're finding the second derivative. Okay, so just keep that in mind. Hot water is dripping through a coffee maker, filling a large cup with coffee. The rate that the water in the cup at time t is changing from 0 to 10 is given by a differentiable function. That just means that we're dealing with a smooth curve, no sharp turns, no holes, no asymptotes, where t is measured in minutes. Okay. Select values of c of t is measured, is given, measured in ounces per minute, given in the table above. So that means 0 minutes, there's no water coming through. 1 minute, it's a very high rate, right? 5.1 ounces per minute. But then as time goes on, it slows to a trickle, right? Where it's only going to come out at 1.2 ounces per minute. Okay, so understand that what's given to you is a rate already, right? This isn't, there's 5.1 ounces of cup in the coffee. This is how much is coming out per minute. Okay, so part A says, interpret the meaning of C prime of 6 and indicate the units of measure. Now, C prime is the derivative of C. What's the unit of measure going to be?
How quickly the rate of water going out changes.
Good, right? And what's the unit of measure going to be?
Ounces per minute.
Okay, ounces per minute. Good. So this is the type of problem that AP exam likes to give, where you have a rate, but it's asking about the rate of that rate. Okay, so like what David said here, C prime of 6 tells us how fast the rate of water added is changing. Okay, so look at that language there. You have rate of water, but you're doing the rate of change of that water, of that rate, right? You're finding the rate of that rate, but you want to be able to say it in this way. It's how fast the rate is changing, okay? It's the rate of a rate at t equals 6 minutes. Okay, units is ounces per minute squared. I think the tendency is sometimes students want to use the language of velocity and acceleration because that just feels more natural, but this isn't a particle motion problem, so that doesn't quite fit in the context of this problem, okay? All right, approximate the value of c prime of 6. Okay, we don't have a c of t function for us to find the derivative, so the next best thing that we can do is just to find the what? Approximate using, right? Derivative is just a fancy word for slope, right? So to find slope, all I need is 2 points. I want to get as close to my source as possible. Sorry, not. So any order pair around this will be sufficient. I can choose these two, I can choose these two, I can choose these two even. I'm going to go ahead and choose these two. Okay, but you can choose others and it will be sufficient as well. So I want to find how fast the rate of water is changing, or at least approximately. So I'll do change in ounces per minute over change in time. So 6 minutes in, the rate that the rate of water is being added is decreasing at negative 0.7 ounces per minute. Okay, part C, interpret the meaning of the definite integral from 1 to 10 of C of t and indicate the units of measure. Now, C of t is ounces per minute. What's going to happen if we do an integral process on top of that? It's just ounces, okay? Now let's think about what's going to happen here. We're accumulating all these rates of water added over that time period. So what this is going to tell us is how much water is added between the 1st and 10th minute, okay? Or the difference in the water level between the 1st and 10th minute, okay? Just to kind of show you a little bit of notation here. First theorem tells us that I can always take the antiderivative, and let's say the antiderivative of lowercase c becomes uppercase c, and uppercase c of 10 minus uppercase c of 1, which just indicate the displacement, right? This tells us how much water is changing between the 1st and 10th minutes. Okay, so this tells us, this meaning is that, okay, this value indicates the change in the amount of coffee in the cup between the 1st and 10th minute. Yes.
So in this case, will the displacement and distance be the same thing? They're going to be a negative value?
Right. In this case, displacement and distance is kind of the same, right? Because there's no backtracking. If that makes sense, right? But in this case, we prefer to use language of that. This is the change in the amount of coffee in the cup between the 1st and 10th minute. Okay. But yeah, in this case, it's going to be how much coffee is added to the cup between the 1st and 10th minute. Part D, approximate the value of definite integral using 2 middle rectangles. So we're going to go back to Riemann sums here. Okay. We're not going to be able to get the exact value because we don't have a function to take the integral of, but we can use our table of values. So 2 middle rectangles. We want to separate our intervals. So remember, you're going to be drawing 2 subintervals. Start at the middle of an order pair, end at the middle of the end order pair, and then you're going to pick up where you left off. The second interval will share the same order pair as the previous one. So we just have to find the width and the heights, right? So the width is subtracting the minutes. 6 minus 1 is 5. 10 minus 6 is 4. Width times height, you want to pick the middle y value. So whatever that middle value is, 5 times 4.2. And then 4 times 1.2. And we get 21 plus 4.8, which is 25.8 ounces. So this tells us that between the 1st and 10th minute, approximately 25.8 ounces of coffee was added to the cup. Notice the unit changes, right? This is our CFT was ounces per minute, but after we accumulate it over that time period, it becomes ounces. Okay, part E, find the average rate of water being added. So this is average value theorem. Okay, so average rate of water, 1 over b minus a, integral from a to b of CFT dt. This is, we can pull that information from part D. It's still an approximation. So 25.8 ounces over a 9-minute period. So if we divide that out, we're back to ounces per minute. So when you're dealing with average value theorem, yes, you are changing the units of measure, but as soon as you do that, you're also going back to where you started from because you're dividing by time again. Yeah. Okay, any questions?
Does it matter if you round it to like 2.867 or if you do a little repeating sign? Does that matter at all?
I would say just in general, just round to 3 decimal places.
Okay.
Yeah, that's the College Board rule of thumb as well. So this is what I think I want us to do. I think it'd be good if we get some more additional practice. So I want to push the test back to Friday, but I don't want to add any days of review. So, but the good thing is, I do want to start the next unit, 5.2 and 5.4. Okay, it's not going to be on the test, obviously, but those two, at least the next 2 days won't cover the entire period. So I can still save the last maybe 15 minutes just to do more review with you. Okay, so tomorrow we'll start the next unit. Thursday we'll continue with 5.4. There's homework assigned, but I'll check it next Monday. Now there's a little bit of a downside. The downside is that we're pushing the test to Friday, right? But the quiz is next Wednesday. So it is going to be a little bit scrunched up. Okay, so just understand that I'm pushing this so that we can get more relief, but then we have a quiz coming up next Wednesday. Okay. Okay, I'm going to adjust the dates for the help session. It's Thursday morning and Friday morning, okay?